Okay, and one last topic for today, for our intro to complex numbers, is the complex exponential. So we're going to see things like e to the complex number, like a plus bi. So now you've seen how to add and multiply and divide complex numbers. You've seen how to differentiate complex valued functions. Now what about exponentiating complex numbers? So first of all, if the usual rules of exponentials are to still hold for the symbols that you see here, which we do want them to, then this should split up as e to the a times e to the bi. So all you really need to be told about is e to the bi. If a and b are real, e to the a, if a is real, e to the a is just what you think it is. It's e to the a, the usual real exponential. E to the bi is a newfangled creature, so we wonder about e to the bi. And here is what we are going to pretty much define it to mean. It's going to be cosine b plus I sine b. So if you take e to a complex number, then you get a complex number, and its real part is the cosine of b. B is a real number, so the cosine of b is an understood quantity. Treat b as an angle and take its cosine. Treat b as an angle in radians and take its cosine. Plus I sine of b. So treat b as an angle in radians and take its sine. Okay, so where is this coming from? Well, if you look at Taylor series or power series for how exponentials worked for real numbers, then force the same kind of Taylor series ideas to apply to the complex situation, then this is what you end up with. And it's really quite amazing how much stuff works when you do it this way. So for example, you may have heard the famous e to the I times pi equals -1. That's a special case of what you're seeing here. E to the I times pi is the cosine of pi plus I times the sine of pi. The cosine of pi is 0, and the cosine of pi is -1, and the sine of pi is 0, so you get -1. So this formula has a really nice interpretation in terms of the complex plane. Remember we said if you have something plus I times something, then we interpret this as a pair of real numbers sitting somewhere in the plane, right, in R2. Well, if you take cosine b comma sine b, which is another way of thinking about cosine b plus I sine b, which is what we decided that e to the bi should be, then that is a point on the unit circle. So this is a unit circle, and it's a point on the unit circle that sits b radians off of the x-axis, off of the horizontal axis, whatever you want to call it, the real axis. So you've got real and imaginary, and if you take b radians off of the real axis, and take a point on the unit circle with that many radians, that point is literally what is e to the bi. So that's just due to the meaning of cosine and sine, right? Like cosine, in the first place, what cosine means is the x coordinate, or the horizontal coordinate, the real part of the point on the unit circle that makes b radians. So that's what cosine b means. And sine b means the y-coordinate of, or the imaginary coordinate, the imaginary part of the point on the unit circle that's sitting at b radians. So of course, if that's what cosine and sine mean, of course we end up with e to the bi is the point on the unit circle that is at b radians. So then e to a complex number, e to the a plus bi, is the following. Interpret the imaginary part as an angle in radians. So this is an angle in radians. And then take the point on unit circle located at that many radians, b radians. And then the a part, don't interpret that as an angle. Just take its exponential. This is the usual exponential. And whatever point on the unit circle you get here, scale that out, multiply it by e to the a. So one thing that's amazing about this is that it ends up capturing a lot of things that would otherwise take forever to write down in terms of trig identities. So for example, if I have e to the z plus w, then that should be e to the z times e to the w, right? If z and w are complex numbers, then this should still work, and it does. But I want you to see what this simple thing encodes, what it ends up encoding when z and w are allowed to be complex numbers. So on this side, we have, let's say z is a plus bi, and w is c plus di. Then on this side, we have e to the a times e to the c times e to the bi times e to the di. And on this side, we have e to the a plus c times e to the b plus d I. So I just split things out. Z plus w is a plus c plus b plus di. So I just split it up. And similarly, I split it up here. Then, we already know that this part equals this part, e to the a plus c equals e to the a, e to the c, for real numbers, a and c. That's not so interesting. So let me get rid of that. Let me just focus on this. This part, that these are equal. So look at what this says. On the left side here, it says cosine b plus d plus I sine b plus d, right? And on the right side here, it's cosine b plus I sine b, that's e to the bi, times cosine d plus I sine d, that's e to the di. And this is multiplication. So to multiply these, you need to use complex number multiplication. So you get, follow this formula we were talking about, this principle that we were talking about way back here. This idea that when you multiply two complex numbers, you sort of distribute and you use the fact that I squared is -1, and you end up with something like this. So when you do that, you will get something plus I times something, and it will involve cosine b, sine b, and cosine d, and sine d. But on the left side, you have cosine b plus d and sine b plus d. This will be a way of stating the sum of angles formula. So what I'm talking about is these angle sum and sum identities, like sine of alpha plus beta is this, cosine of alpha plus beta is this. These things, you don't have to worry about these anymore because they're just sort of contained in much simpler looking statements that are statements about complex exponentials. So if you work out what this is, you will see that it's a way of describing that identity. But you don't have to actually work with that identity in practice so frequently. And if we didn't do this, if we did not bring complex numbers into the picture, then you would be going to this page using these identities constantly in differential equations, and it would be super annoying, and it would be a lot harder to see that certain obvious things are true. Everything would be obscured underneath all the notation. So that's why we're using complex numbers.